Hi, today we are going to talk about modern physics. Now, this is a topic of physics which has the greatest ROI. ROI means return on investment. Okay, so whatever time you're going to invest in this chapter, you're going to get the maximum return because compared to other chapters of physics which you might have gone through, you know that modern physics is really easy, right? Again, I'm talking relatively. Now, modern physics basically has these three chapters. It has dual nature of matter, then it has atoms, and then it has nuclear physics, all right? And in this session, what we are going to do is we are going to briefly go through all these three topics, and I'm going to discuss what are the major things we need to cover in each topic. And again, I want to put this as a disclaimer that if you are going to write JEE, please do not leave these three chapters, okay? And if you are like rushing up with your preparation for other chapters or whatever is the reason, don't leave these three chapters because they're like free marks, because not just that they're easy, but they are also very less time consuming, in the sense that when you're writing an examination, like if there's a question which you can just see the question and answer it like in 1 minute, then you're basically saving your 2 minutes, which you can use it on a tougher question, okay? So it just doesn't give you marks, it also gives you extra time. So that's the thing with modern physics. Now let's start with dual nature of matter, all right? So in physics, in dual nature of matter, what you have basically is photoelectric effect. The entire chapter revolves around photoelectric effect, and there is nothing else than photoelectric effect basically in dual nature of matter. And what is photoelectric effect? I'm going to discuss that. Now what happened is in the early 19th century, what happened, there was this guy called Maxwell, and he developed this theory of electromagnetic waves, basically electromagnetic theory. So he said that light, which was had been a mystery, he said that light is basically an electromagnetic wave. What does that mean? It means that it's a wave which moves such that it disturbs the electric field and magnetic field in that medium, or it moves because there's a variation of electric field and magnetic field. And people were completely convinced that light is a wave because it showed wave-like properties like interference and diffraction. And there was not a speck of doubt in the minds of people that light could be anything other than a wave, okay? Now what happened, this guy called Hertz performed an experiment, and he found very strange results in this experiment, okay? What he found was, if you keep a plate, okay, a metal plate on one end and another metal on other end, and you connect it in a circuit, and you shine light on it, what happens? You see that there's a current flowing in that circuit, although nothing is connected in between, okay? You know the setup of photoelectric effect. Now the question is, fine, the first guess which would have come in the minds of the physicists back then would be, okay, so what must be happening is this light is coming in the form of waves, and this wave is coming and there are electrons inside, and an electron must be absorbing the wave, and it will just sit there and absorb enough energy, and when it has enough energy to come out, because you know that you need to provide some energy to the electron to come out of the atom, then it would come out, because electromagnetic wave is nothing but a form of energy. You know that when light moves, that wave moves, it transports energy. In fact, any wave where it moves, it transports energy and momentum, right? So it was very clear this is what it must be doing. But then when he changed the certain parameters of his experiment, he found something very strange, okay? He found this, that if you're using a light of a particular frequency and you're seeing that this phenomenon is occurring, which is called photoelectric effect, because photo is light, word related to light, okay? It was not called photoelectric effect back then, I guess, but whatever. So he observed that this effect is happening for a certain frequency, okay, for a certain mu. But when you lower the mu, at some point this phenomena stops happening, okay? And if you keep it below that mu, that whatever mu value you have found, whatever the threshold frequency you have found, if you keep it below, then what happens? Even if you are increasing the intensity, no matter how intense you make that wave, your electromagnetic wave, you see that no electrons are coming out. Now this was very counterintuitive, okay? People were like, this cannot happen, because we knew from our understanding of waves that that intensity is related to energy of a wave. The more intensity a wave has, the more energy it is carrying, right? So, okay, fine, you're using less frequency, who cares? You increase the intensity, energy increases. If energy of the wave increases, then electrons would have enough energy to suck from the wave and come out. Why aren't they coming out? Okay, so it seemed that there is this limiting frequency, there's this threshold frequency, and only above this frequency, no matter what the intensity is, you don't give a care in the world about what the intensity is, the electrons will come out. Below this, electrons won't come out for a particular metal. Okay, this was very crazy. But then, okay, fine, all right, after this threshold frequency, electrons will come out. Now what? You choose any of that frequency. Okay, fine, I fixed the violet frequency. Okay, now at violet frequency, I'm looking at electrons are coming out. Now what? Now if you increase intensity, right, what is the thing which is changing? They found that when the electrons are passing through this circuit, right, you can imagine that electrons are hitting this metal and this passing to other metal, and they are completing a circuit, and there's a current flowing and there's an ammeter. They find that when you increase the intensity, the ammeter is showing a greater reading. It means that current is increasing. When current is increasing, it means that basically what is increasing is the number of electrons which are coming out. So they were like totally baffled. Okay, increasing intensity increases the number of electrons coming out, and frequency has this crazy behavior that there is a threshold frequency below which the electrons are not coming out at all. Okay, and one more thing, that another thing was that, see, if light was a wave, right, and an electron is like someone who's like ready to like sit there and like absorb that energy from that wave, then there is this minimum energy it requires to come out. So it will sit there and the wave would come, it is sucking that energy, but it will take some time to it to suck enough energy to come out, to absorb enough energy to come out of the atom. But what we found here is that as soon as you switch on the light, instantly the electrons are coming out. They're taking no time at all, right? Almost like a nanosecond, 10 to the power minus 9 seconds is the range in which it comes out, but that's almost instantaneously. Why is this happening? Why is it not taking any time? What on earth is happening? So nobody was able to figure it out. Okay, and the classical electromagnetic theory, which was prevailing till then, was kind of becoming shaky because no one was able to answer why this phenomena is happening. No one is understanding this, and this was in the late 1800s. Then came a guy, I am sure you have heard of him, called Albert Einstein. 1905, published 3 papers, one on Brownian motion, one on special theory of relativity, and one on photoelectric effect, won a Nobel Prize on photoelectric effect, by the way. And he explained this. He said that let's forget, just completely unlearn the fact that a wave is basically a light is basically a wave. Let's forget that. Okay, let's assume that light is made up of small particles. Now what? He said that if you assume that light is made up of small particles, and each particle of this light has an energy which is proportional to its frequency, right? And it's a packet of light, right? So it's a packet light, you can either, so an electron has a choice. It can either take the whole packet or it can take nothing. Okay, it cannot take half a packet. That's the condition. Okay, so he said that. So now whatever energy that that electron requires to come out, let's say that the frequency which corresponds to that energy, by the way, Planck gave this thing that energy is related to frequency. Energy is equal to h times nu. It can be expressed in terms of frequency of a wave, which kind of comes simultaneously. It's kind of a very cyclic thing which was going on back then. But basically he said that, let's say whatever energy that electron requires, let's express that as h times mu naught, right, is equal to the E, that is the energy which is required. He said that if the mu of our wave is more than that, more than h times mu naught, it means that my packet is big enough to take that electron out. Okay, and if it is exactly equal to h mu naught, it will just take it out, but it will not impart it any extra energy. That's what he wanted to say, that there are these balls coming, and each ball has an energy of h nu, and the energy which you require is h mu naught. You subtract these two energies, the extra energy which you gets reflected in the form of kinetic energy of that electron. Okay, so kinetic energy is equal to h nu minus h mu naught is what he was saying. And it also makes sense because as soon as that ball of energy hits it, which we now call photon, the electron will come out immediately. All right, it made a lot of sense. And then he said that what about the current was increasing? I saw the current was increasing, was increasing intensity. What about that? He said that basically when you're increasing intensity, you're not increasing the energy of one of these packets. The energy of this packet is fixed because it is related to frequency. It is h times mu. You're increasing intensity. That means that you're increasing the number of these balls, number of the photons coming out. If more number of photons come out and hit the target, more electrons will come out, hence the current is increasing. And this is how he explained what was happening, and this is called the photoelectric effect. And after this, it was established that light is a wave as well as a particle. Okay, so light has this dual nature. It is neither a wave nor a particle. It is also a wave and also a particle. Okay, so sometimes it behaves like waves, sometimes it behaves like particle, and depends on what situation you put it into. So it gets to decide. So in photoelectric effect, it behaves like a particle. So this is the basic theories, right? So kinetic energy is equal to h nu minus h nu naught. Now what they did, fine, this is understood that this is what happens. Now this is the plate, electrons are coming out, fine. Now let's say h nu was the energy you gave in, h mu naught was the energy required, h nu minus h nu naught is the kinetic energy with which the electrons are coming out. What I do is I put another plate on this end and I give it some positive potential. Now what will happen? Positive potential will attract these electrons towards itself, right? So because of this positive potential, electrons are getting attracted, pulled towards itself, towards this plate, right? Now what will happen? So if you keep increasing this positive potential, more and more it will pull. But we found that no matter how much you increase, the current which is increasing, because the more fastly if it comes here, more current will be there because it is charge passing per unit time, right? So the thing is, if you keep increasing the positive potential, it will pull it strongly and strongly, right? So the current must increase. So it kept on increasing for a while, but after a while it became saturated. Right? After that, it was not increasing much. So it is called a saturation current. Right? The current cannot increase more than that. But that's not very fascinating. What is fascinating is when you make the potential zero of this thing, and not even that, when you make the potential negative. When you make the potential negative, what will happen? This plate will start repelling the electrons back. I don't want you. You go back because I'm negative, you're negative. Alright. So this plate wants to repel those electrons. Now what? So okay, fine, you made it negative, but still there is some current. It is trying to repel, but it is not completely able to repel it. And you make it more negative, not completely. So you reach a point, okay, where you have made it enough negative that the electrons are not able to reach it at all. It means that even the electron with the maximum kinetic energy is not able to reach it, right? That potential is called as the stopping potential. Appropriately named, of course, stopping potential stops it. So stopping potential, if that is, let's say, minus V, then that is the potential required to stop the most potent or the most kinetic energy holding electron. So Ke max will be equal to the potential difference, let's say Vs times the charge E, because you know that E into Vs is the energy which gets consumed in that potential difference, right? And well, something goes from a lower potential to higher potential. If the potential difference is Vs, then E times Vs is the energy difference. You know that you have learned this in electrostatics. I'm not going to elaborate on that. So basically what's happening is E times of Vs is the energy required, and that must be equal to kinetic energy max. So even the maximum kinetic energy holding electron will not come to it. So this is then cracks the basic idea of photoelectric effect, all right? And questions are asked based on this, that this is the threshold frequency, this is the frequency with which is coming, what is the maximum kinetic energy, what is the stopping potential, what is the graph between this and that. If you keep the stopping potential constant, if you keep the frequency fixed, if you increase intensity, what will increase? The saturation current will increase, because you know that intensity increases, saturation current increases. If you fix the intensity, if you change frequency, what will happen? After frequency, no photoelectric effect. After and like before that frequency, no photoelectric effect. After that frequency, photoelectric effect will start taking place. And if you keep increasing the frequency, what will happen? That the maximum kinetic energy of the electron is increasing, because Ke max is equal to h nu minus h mu naught. Right? So every electron is getting some extra energy along, like, because h nu naught is already consumed in like trying to take it out, but it has still extra energy left. So more frequency, more extra energy it will have, and more will be the stopping potential. To say like it will be more negative, that's what I mean. Okay, so this is the whole theory of photoelectric effect, and this is where the whole chapter of dual nature of matter revolves. Now there's this guy called de Broglie. He was a really funny guy. He gave a hypothesis called de Broglie hypothesis. Sometimes people call it de Broglie's hypothesis, but it's pronounced de Broglie. So de Broglie said that nature loves symmetry. What are we seeing is waves behaving like particles. Why aren't particles behaving like waves? Okay, and he gave this hypothesis that matter behaves like waves and the momentum is inversely proportional to its wavelength. And that's also one of the things which is there in your syllabus. P is equal to h by lambda. So that is also one very simple equation. Very simple one-liner questions are asked on that, so I'm not elaborating too much. Why I said de Broglie is funny is because when Einstein opposed this whole idea, he also said that I'm wrong or something, but later it turned out that he was right, so it was all very funny deal. Now what happened is, all this was happening simultaneously. A model was being built as to how an atom looks, and this is what takes us to our next chapter, which is atoms. Okay, now when you go to atoms, you start with J.J. Thomson. Basically this is all theory, not a lot of questions are asked, but J.J. Thomson was like, what we had seen is when we heat metals, these particles of negative charge come out. Okay, so he wanted to make a model of how the atom looks. So he said the atom is like a watermelon. Okay, it's like a melon, and the whole melon part of it, the juicy part of it, is just the positive part, which is like this whole sphere, and electrons are these like seeds embedded in that sphere. Okay, it's also called a plum pudding model and all those models, and the electrons come out, but we found out that it was wrong because Rutherford did an experiment, and that is an important thing. He did a gold foil experiment where he kept a gold foil and he shot some alpha rays. Alpha rays are basically helium nuclei, right, which are positively charged. So helium nuclei, he shot at them at the gold foil, and what he found was most of the helium nuclei or most of the alpha rays just crossed through. Okay, there's no deflection, nothing. Okay, so he concluded that it cannot be this ball of positive mass. It turns out that most of the atom is just empty. Most of the atom is empty space. Okay, and then he found that 1 in like 1,000 turned by 90 degrees, like deflected by 90 degrees. Some of the alpha rays are deflecting, and maybe 1 in 10,000 or 20,000 was deflecting by 180 degrees. So he found that most of the atom is empty, and whatever mass an atom has, everything is concentrated at a point which we call as a nucleus, which is the center of that. Okay, and it is very, very tiny compared to the whole size of the atom. And he said that the electrons are basically these really tiny things which revolve around this nucleus, and the size is so unimaginable. You know, the nucleus is 10 to the power of 5 times smaller than an atom. So imagine a big football field and a small tennis ball kept in the center of the football field. That is the scale of the nucleus and the atom. Okay, and imagine the electrons to be small pinheads revolving around that stadium. So that is the scale of an atom. That was the Rutherford model, and it was a pretty successful model because it was showing things experimentally, that whatever is right or what. But then what happened, people thought more on it, the theoretical physicists, and they felt that this cannot be right because according to the electromagnetic theory, which was developed by Maxwell, whenever an electron is accelerating or any charge is accelerating, it loses energy. So an electron moving around a nucleus must be losing energy, right? And if it is losing energy, what will happen? It will spiral. If we work out the mathematics, it spirals inwardly and should embed inside the nucleus. And if that happens, atoms cannot exist. And if atoms cannot exist, the universe could not exist, and me and you would not be here to talk about it. So what is happening? So that was one of the major drawbacks of Rutherford model, that it could not explain. There was basically an inconsistency with the electromagnetic theory, which was a very well proven theory at that time, and a very well experimented with theory. Now what? No solution. Okay, but he could not also explain what is the pattern in which these electrons are revolving. Are they revolving randomly? Is there any pattern? Is there any particular configuration? What is the system going on there? He couldn't explain all that. For that came our next hero, Bohr. Okay, so Niels Bohr said that well, I don't know why exactly are they revolving, okay, and why exactly are they not losing energy as the electromagnetic theory predicts, but I have found a pattern. That's what he said. What the pattern is, that I found that they are orbiting in certain very particular orbits, okay, particular states. And he called them stationary states because only in these states it is not losing energy. Anywhere else it is losing energy. Cool. What is the property of that state? How were you defining that state? He said that the states are such that if you look at the angular momentum of the electron in that state, you'd find that it is an integral multiple of this number h by 2 pi, where h is the Planck's constant. You know the Planck's constant, right? 10 to the power 30 minus 34 and all that, 6 point something. He said that if I find the angular momentum, that is mvr, right, that is equal to n times h by 2 pi. Only if this condition is satisfied, because you know every orbit will have its own mvr, its own angular momentum. So only the orbits which have this particular condition fulfilled will be allowed to be stationary, are allowed to be stationary for some reason. Okay, I don't know what that reason is, but this is what seems to be true. All right, and fine, does it work for all the atoms? No, it doesn't work for all the atoms. It works only for hydrogen. Cool. Or any atom which has only one electron. So a lithium ion would work, a helium ion would work. Okay, but if you have more than one electron, Bohr is like, dude, it's not working. All right, so that was the Bohr model, and this is what he told. But then people started thinking, why is this happening? I mean, like, what is this special thing? Then someone came up with this idea, and this is where Broglie also comes in, that if you imagine an electron moving around this circle, not as an electron but like a wave. This was a crazy idea. People would have thought that people who are thinking this are like absolutely insane, because why would a particle want to be like a wave? But he said, let's imagine, okay, for the sake of imagination, if an electron was like a wave. All right, so what? So if a wave wants to be in a what do you call it, when you have a string and two ends are fixed, you get these standing waves, right? If it has to be a standing wave, then the condition is that the whole circumference, which is 2 pi r, must be some integral number of the lambda by 2, because only integral number of half wavelengths must be possible, right? You can imagine if you try to make a complete wave in a circle, a complete wave, then you can count 1 half wave, 2 half wave, 3 half wave, 4 half wave, 5 half wave, 6 half wave, like that, n half waves, right? Only then it will be stable. So that if you imagine that, then it seems that from here you can derive this condition which Bohr is telling. Seems like electron behaves like waves, and this is where the Broglie got his idea that matter must be wave, and this is where one of the theoretical foundations for quantum mechanics was set. Okay, so that is the whole idea of Bohr. Okay, and you know the drawbacks of Bohr, that it could not, and plus there was another thing, there's another line of thing which is going on, which I'll tell you. So this is all like a story. Now another line of thing which is going on is this. Now you take a metal, you take any object, you heat it, okay, and then when you heat it, what happens? It gives off a lot of electromagnetic waves, electromagnetic radiation. Cool. Now what you study this electromagnetic wave, there are like infinitely many electromagnetic waves coming out, right? But you can study what are the different frequencies they have. So you find that any ordinary thing which is like, for example, this light is there in our studio, and it is like reflecting light, and if I just want to find out what all frequencies are present, I would find that almost all frequencies are present. There's like a mixture of all the frequencies are there. Okay, but they found this very strange thing, that if you take a particular gas in a chamber, okay, say hydrogen or whatever, and if you heat that gas, and there's nothing else, just that gas, and you let it radiate, okay, nicely you let it radiate, you find that it is radiating some electromagnetic radiation. Then you try to check what all wavelengths or frequencies, same thing, are present there. You find that only some particular wavelengths are present in the thing which it is radiating, the thing which it is emitting. So if you want to make a spectrum of all the wavelengths which are present in its emission, which is called an emission spectrum, you'd find that only certain frequencies, certain wavelengths are present. So you find that 1 line, 2 line, 3 line, 4 line, like line by line things are present. That is called line spectrum. Okay, people were not able to understand why this is happening. Okay, or let's say if you don't heat it, what do? You pass some white light through it. Okay, some white light which is a mixture of all the frequencies. You pass some white light through it. You find out the other end that all the white light is coming back except for certain frequencies. Those frequencies which it was emitting, now only those frequencies are missing out. So entire spectrum is present, red, violet, everything, infrared, ultraviolet, everything is present except for those particular frequencies which it also emits in other case. So now what you made some violet, you made it absorb some white light, called as absorption spectrum. Okay, so basically these experiments are not important. The crux of this is that it seems that these atoms of these particular gases are releasing or emitting only certain wavelengths of light. Why is that happening? Okay, that was one of the questions. And there is also something called a Zeeman Effect, which is not there in your syllabus, and there is no point of discussing all that. But basically, why is this happening? So we learn in this chapter of atoms is that basically this happens because, see, there is this nucleus, okay, and around the nucleus there is one electron in one orbit, another electron in another orbit, the other electron in another orbit. Using the equations which you get from Bohr, we found out how much is the energy of each orbit. So the energy is minus 13.6 n square by z, or z by n square. I keep forgetting it is z square by n square, right? Please remember this. Minus 13.6 z square by n square is a formula which you need to remember. Okay, that is the energy of the nth shell of an atom which has atomic number of z. So they found that every shell has a particular energy, right? The first one would have, for an hydrogen, would have minus 13.6 electron volt. Electron volt is another unit. 1 electron volt is equal to 1.6 10 to the power of minus 19 joules. Okay, so the first orbit of hydrogen has 13.6 electron volt energy. The second one has minus 3.4 electron volt energy. The next one has minus 1.5 electron volt. So some numbers are there. Now what? So it means that only an electron with that particular energy is allowed to move in that orbit. Okay, only an electron with a different energy is allowed to move in another object. Like 13.6 energy electron can move in the first orbit. Now what happens? Electrons can shift from one orbit to another orbit. Okay, fine. So what? But when they shift, they have to pay. So now the first shell is 13.6, first orbit, minus 13.6. The other one is minus 3.4. So if we find the gap is 10.2, and the other one, the second one is at a higher energy, right? Minus 13.6, minus 3.4. So the gap is 10.6, 10.2, right? 10.2. Cool. Now what happens? If an electron from the lower one wants to go to the upper, it needs to pay how much? 13.2 electron volts. So only when it has when you give it 10.2 electron volts, only when it gets 10.2 electron volts, it can jump up to a higher energy level. Okay, and if one from a higher energy level wants to come back to the initial energy level, then it will release exactly 10.2 electron volt. Okay, what does that mean? It means that there are different levels of these electrons, and when an electron transaction happens from one level to another level, it can release only this perfect number of energy, like this perfect value of energy, 10.2 or whatever is the energy gap between those two shells. Okay, it cannot, and the energy transaction cannot be of any random number, only whatever is the gap. Okay, so what happens is when you heat these gas in the emission spectrum, what happens is first the electrons absorb the phonons at the exact frequency which allow them to go to some higher state. But when they come down, they will come down to only one of the allowed states. So they will only give out this fixed energy, and that fixed energy is associated with the fixed frequency, right? E is equal to h nu. So only certain frequencies would come out of that atom. Not all the frequencies would come out. Okay, and hence you're seeing these lines in your emission spectrum. Okay, so that is the emission spectrum. And another things which you get from Bohr model is that the radius is 0.53 n square by z, and the velocity is c by 137 z by n. Please remember these values because they ask questions on these values. All right. So that was Bohr model in your atomic structure. And that is basically it. And then when you go to chemistry, you also learn that there was something called as quantum mechanical model, and which is not there in physics. This is basically atomic structure. Okay, so the next chapter in modern physics. So what you have to take care here of basically the Bohr model and how the energy transactions happen. Next chapter is nuclear physics. Now nuclear physics is another not very difficult chapter, but the concepts are a little tricky to understand. First thing is, we are going to use the famous Einstein equation E equals to mc square, that mass can be converted into energy and vice versa. Okay, so what happens is, when a nucleus is formed, what happens, let's say these are two nucleons, like the particles which make up a nucleon. This has an energy of x, this is an energy of x. They both have nice energy x, or not energy, mass. So this is a mass x, this is a mass x. They both have masses x and x. Now what happens? They come together to form a nucleus. Okay. When they come together to form a nucleus, they lose some mass in the form of energy. Okay. They lose some mass in the form of energy, and unless you provide that energy back to them, they cannot be separated as their individual atoms, individual nucleons. Okay. That is the whole idea in this chapter, that if you have any nucleus, right, and there is the mass of this nucleus, the mass of the nucleus, if it's a stable nucleus, will be less than the sum of the mass of its constituents, because when the constituents came together, they lost some of their mass. Okay, so that is the whole idea which revolves around this chapter, and you get these equations where this plus these many nucleons were added to give this nucleus. How much energy change happened? So all you have to do is the final energy minus final mass minus the initial mass. The final mass will always be less than the initial mass. Okay, and like that, you whatever is the mass, you calculate the mass defect using this, that what is the difference in the mass, and you multiply it by c square, then you get what is the energy change that has happened in this process. Okay. Then you have these nuclear reactions. You have uranium-235 disintegrating into this and this, and so and so. So you get these you discuss about these particles called alpha particles, beta particles, and gamma particles. Alpha particles are basically helium nuclei, which are positively charged and mass of 2, charge of 2, mass of 4. And then you have beta particles. Beta particles are nothing but electrons, and gamma particles are nothing but electromagnetic waves. So when something releases a beta particle, its atomic number increases by 1, because beta particle is -1. So on the bottom subscript is the atomic number, superscript is the atomic mass, right? So you just have to balance. So in that, if you are given any radioactive equation, you have to balance the superscripts and the subscripts. They must be balanced on both the ends. Now, whenever a beta particle is released with an anti-neutrino, and whenever an electron is released, it is released with a electron is basically beta particle, so it is released with an anti-neutrino. And whenever a positron, which is an anti-particle of electron, which has the same mass but positive charge, it is released with a neutrino, which is basically what it is not in the scope of this chapter, but I would really want to discuss it sometime. So it carries energy, basically. That's what it does. Now, in this chapter, the part from where some serious questions are asked is basically on nuclear disintegration. Okay, so nuclear disintegration happens in such a way that if you have like a collection of nuclei somewhere, then what happens? The rate at which those nuclei integrate is proportional to the number of nuclei present. Okay, dn by dt is proportional to n. And using this principle, we find out that the number of nuclei left at any time in that bowl is equal to the original number of nuclei, which is n0, into e to the power of minus lambda t, where lambda is called as the decay constant. So this is the famous radioactive decay formula. N at any time t is equal to n0 e to the power of minus lambda t. Okay, so using this at any time t, you can find how many number of the nuclei are left. Okay. Now another very important thing which is asked in this chapter is half-life. Okay. Now if you see this formula, n is equal to n0 e to the power of minus lambda t, you would know that it will take infinite time to make the total number of nuclei 0. So the total integration takes almost infinite time. So, but you can find the half-life. Half-life is whatever you began with, how much time it takes for it to become half. Okay. So you find that the half-life of any nuclear sample is given by log 2 to the base e divided by lambda, which is the decay constant. So log 2 to the base e is 0.6, approximately 0.69 or something, divided by lambda gives you the half-life of that thing. So for example, if you have, let's say, 100 nuclei, and it is said that in 3 days they become 50, then the half-life is 3 days. Okay, so in 3 days they will become 50, but in another 3 days it will become 25. From 50 it will become 25, and then from 25 it will become 12.5, which is not possible, but usually the number of nuclei is very large, so this problem doesn't arise. So that is one thing. So Shri Devi is asking how fluorescent works. That is actually not in the scope of modern physics, but fluorescent basically works on the reaction which happens between these two things. I think I would take some question which is relevant. Okay, so there are not a lot of questions. Fine. So let's continue with nuclear physics. So now what happens is, so once you understand that what half-life is, you can solve a lot of problems without actually approaching the equations. Okay, so for example, let's say it is given that something becomes this much. So in one half-life, something becomes half. Okay, the original thing becomes half. In two half-lives, it will become half of half, and it will become 1/4, right? In three half-lives, it will become half of half of half. That is 1 into 2 to the power of 3. In four half-lives, it will become 1 into 2 to the power of 4. Like that, as the number of half-life increases, n naught becomes n naught divided by 2 to the power of n. Okay, so this way you can find number of half-lives that has happened after a particular time. Okay, so this is also one of the ideas which you use to find half-life. So given the time constraint, I cannot discuss a lot more things about all these three chapters. I guess I have given you a good revision of all these three chapters, and I hope that you do well in your exams. Now again, I want to repeat that please do not skip modern physics, because modern physics is one of the most paying topics. If you go through all the topics, it will not take a lot of time, and if you solve some problems, you would find that the problems are much easier compared to the other problems of physics, and a lot of questions are asked in almost all the question papers, all the tests which are conducted all over the country. And so prepare well. Sridhama is asking what are beta particles, what is the charge of alpha particles? Justify. Okay, fine. I have already told you that beta particles are nothing but electrons. That's just a fancy name for electrons. Alpha particles are helium nuclei, which has a charge of 2 and a mass of 4. Justify doesn't make any sense. It's just that the nucleus is named alpha particles. Okay, if your name is my name is Himanshu, and someone comes and asks me, justify your name? There's no justification. It's just someone gave that name. So thank you for joining us today on this live. I hope you got something solid from this discussion, and please visit our YouTube channel, right? And there are some very interesting videos there. You can watch them. They're animations. If you find some topic dull, it might entice some interest inside you. And there's a link in the description to download our app. Download our app. It's free for a week. You can use, and you can see and what all things we are doing. And hopefully it will all be very helpful, and all the best for your exams.